Hello and welcome to this clip covering the 2014 C3L6 paper, question 2. I'd like to point out that this clip isn't a mark scheme, it's just a few ideas from me on how I might go about completing this question. If you wish to refer to the past papers and their mark schemes, together with some comments from the examiners from each year, you can go to www.c3l6.com. So you can see that there's quite a conspicuous box on the top sheet. You'll find this on every single Cambridge Chemistry Challenge paper. And it's designed to get you to think about using a problem-solving approach rather than trying to remember lots of things from your A-level courses. That's what your A-level exams are for, the factual recall together with some deduction. This is almost entirely deduction and application. And finally, don't forget your good mathematical practice. Things like calculation layouts, an appropriate number of significant figures. In other words, the smallest number of significant figures that have been quoted in the data provided in the question. And finally, an awareness of units and their appropriate conversions. Okay, there's one more thing to have a think about before we get cracking with the question. So this periodic table comes with the paper, and you might notice that some of the AR values, the relative atomic mass values, have a larger number of decimal places. You need to use these values, not ones that you might have remembered from your textbook, from your A-level textbook or your exam board's periodic table. Calculations in the actual paper will expect you to use these values. So this question is about a real-life environmental disaster which actually happened in India around the time of this paper. So it's about a drug called Diclofenac, and this is an anti-inflammatory. It's in some pharmaceuticals that are used by humans, by us, but it's also can be used in other species as well. So it's a drug given to cattle by farmers which combats inflammation. Now what happens when the cattle die is the vultures feed on their bodies. Vultures are obviously found naturally in the subcontinent. So this substance interferes with the vulture's kidney function, so ingesting it's going to be extremely toxic to them. And it wasn't until large numbers of vultures started dying that the connection was made between the use of this compound as an anti-inflammatory in cattle and the mortality rate of the vultures that has suddenly been noticed. So this question deals with the synthesis of the compound diclofenac, and it says that there's a skeletal formula being used. You can see up in the top right-hand corner I've put some things from the previous screen because it links to what's going on this page. So in case you haven't come across it yet, benzene is notified by a hexagon with a circle inside it. And you can see that there's two compounds that are precursors or starting materials for the synthesis of diclofenac. You've got 2,6-dichloroaniline, and you've also got 2-chlorobenzoic acid. So the first part is pretty straightforward. All they wanted to do is to work out the molecular formulae of these two structures. So the question already told you that benzene is C6H6, so all you have to do is replace H with the substituents as appropriate. So when you write out the molecular formulae, you write out the carbon and hydrogen atoms from the main chain or ring first. Then you can list all the other atoms in alphabetical order. So what we need to do is put together an equation using compound 1, compound 2 and KOH to give compound A. So if we put the information that we have together, you can see that from the information that we're given, there's H2O, KCl, and the KCl, H2O, and compound 1, compound 2 are all in 1 molar ratio, so 1 to 1 to 1 to 1. So, bearing that in mind, it must be that compound A is a combination of compound 1 and 2, but with H2O one hydrogen removed. So therefore we have to think in these terms when we're trying to deduce the structure, the formula for compound A. So we now have a formula of compound A. So from the infrared data for compound A, it also tells us that COOH is still intact. So therefore the carboxylic acid group in compound 2 can't have reacted with KOH. So the only other functional group which possesses a hydrogen atom that could react with OH- from KOH is the H2N. So what must have happened is the copper catalyst allowed the removal of Cl from compound 2 because you have KCl as your products. So this gives us that structure as compound A. So in part B, as if compound A is treated with LiALH4 followed by HCl aqueous instead of H2O, compound B is isolated as its hydrochloride salt. And in the salt, the most basic atom in the molecule is protonated by the HCl. And what they want is a structure for the hydrochloride salt, including both the positive and negative ions, clearly indicating which atom is protonated. So nitrogen is the most basic atom in that particular compound because it's got 3 bonds and it's analogous to ammonia. And if we remember that HCl dissociates in aqueous solution into H plus and Cl minus, we can start to now see where the H plus will go and where the Cl minus will go. So that allows us to draw out the hydrochloride salt with both the negative and the positive ions. And I put the structural formula at the bottom to help you visualize what I mean. Okay, so the next part, part C. So in part C, the first part describes ALH4 as a source of H-. Now if we think about H-, might not have come across it before, but it's a species that has a negative charge. And if it's got a negative charge, this means it must have a lone pair of electrons, which may be available to create a dative covalent bond. If they do this, if a dative covalent bond is created using this lone pair of electrons, then that means you'd have a nucleophilic attack going on, so H- must be a nucleophile out of the choices you've got. In the second part, it asks you to classify the reaction of compound A to compound B. If you look carefully at the changes of the functional groups, apart from the actual creation of the NH bridge between the 2 benzene rings, you have a COOH in compound A that gets changed into a primary alcohol, an OH, in compound B. Now if you do the reverse of this, an OH going to a COOH would be an oxidation, according to our work in alcohols chemistry in our first year. So therefore the conversion as described must be a reduction. So let's now move on to part D. So this part of the question asks you to visualize the compounds we've just looked at. But in your mind you need to replace the H atoms with D atoms. So let's look at the 2 options that we've got. We've got to consider reaction I and reaction II. In other words, creating compound B1 or compound B2. So your first option carries out the reduction using LiALH4 first, before converting all the H to D. The second option carries out the reduction using LiALD4 before using H2O, which would mean no further conversion of H to D. So it's important to remember, if you look at all the structures, that you don't actually change the aromatic hydrogens into deuterium. So in the first option, creating compound B1, the COOH is reduced to OH, and then D2O comes in and converts that OH into OD and the NH into ND. So when creating compound B2, using LiAlD4, you get the COOH group reduced to CD2OD, as shown, using LiAlD4. And the NH remains unchanged because the H2O is used afterwards, not D2O. So in part E, the first part of it, it talks about sodium cyanide, and it talks about the C triple bond N minus anion, and it asks you to classify that anion as either nucleophile, electrophile, radical or catalyst. So for reasons that we've already been through, you would also classify this as a nucleophile because it's negatively charged, which means it's got a lone pair, which means that can actually engage in a dato-covalent bond. So then what it asks you to do is suggest structures for intermediate compounds C and D. So to do this part, we need to refer back to the previous reaction scheme that was on the prior page. So we now know that Cn- is a nucleophile. So we also need to have quite a sharp think about what the infrared information tells us, because particularly if you're doing this as a first year student, you might as well come across the action of Cn as a nucleophile. So thinking about compound B, compound B has a OH group. That means a polar CO bond. It also contains an additional chlorine atom. It's got 3 chlorines and B has 2 chlorines. So a chlorine has been added between B and C. So I'm going to make an additional sort of stab in the dark here. The peak at 2230 centimeters to the minus 1 could be formed from the nucleophilic substitution of Cn for that chlorine. So if you think about the things that could be replaced by Cn, so nucleophiles need to attack polar bonds. They won't attack it unless it's polar. So how would you have a polar bond? If you look at the molecular formula of compound C and compare it to compound B, the OH is gone. So there's no OH, so there must be a Cl instead. So the position of the OH in compound B must be substituted by a Cl. And that Cl can be substituted further by C triple bond N. So that gives us the structures for compound C and compound D. Let's now go on to part F. So part F asks us to assign all of these different peaks and absorptions to functional groups or particular bonds. So we can work out some of the more obvious absorptions if we just refer back to the reaction scheme. However, we've got 1604 and we've also got 3320 to 3390. And these are both in the sodium salt of Diclofenac. So therefore, if you look at the 1604, that will still be a C double bond O. But this time it'll be in a carboxylate form because the sodium salt will look something like that. So the 3320 to 3390 sharp must be the NH because that's found in all the compounds and in none of the compounds has NH been changed. So therefore that completes all 5 of our absorptions. So part D is part G I should say, is very straightforward. They want you to draw all the isomers of dichloroaniline where both chlorine atoms are attached to the benzene ring. So the first set of isomers come from moving the second chlorine from position 3 to position 4 and then position 5. So if you consider all the different possible combinations of positions for the chlorine atoms, all the structures can be deduced. So let's now go on to the next page. So this is the final section now. So this section is about the mass spectrum of diclofenac. So I'm going to just copy over the structure of diclofenac. So it says the most abundant ion had a formula of H10Cl2NO2. So the ion must be diclofenac minus a hydrogen. Now don't forget it's a negatively charged ion, but they've already explained in the question that this particular mass spectrometer produces negatively charged ions. So looking at the structure, the only part of it that could easily lose a hydrogen is the OH. So therefore the structure must be the carboxylic acid converts into a carboxylate, which gives us a structure that looks a bit like that. So in part I they asked you to consider the most abundant peak from this anion. So it's got an M/Z ratio of 294 and it's due to the lightest isotope of each element being present. So C12, H1, 35Cl, 14N and O2. It gives you the isotopic abundances of 2 carbon isotopes and 2 chlorine isotopes. So the most abundant ion will be comprised of the most abundant isotopes. And we're also told to use the lightest isotopes in each case. In other words, carbon 12 and chlorine 35. So to get the percentage peak height for our anion, we need to take the abundance of each of the lightest isotopes and multiply them by each other, but using the abundances expressed as decimals, not percentages. So we need to raise each decimal that we're writing to a power, and that power is the number of atoms of that element present in the anion. So there's 14 carbons and 2 chlorines. So that gives us 0.492 or 49.2%. So for the anion to have an MZ of 295, you need to substitute one of the atoms with an isotope 1 mass number heavier instead of 294. So you swap a carbon 12 for a carbon 13. So once you do this, you can then substitute that carbon 13 into the formula that you had before. So you have 14 carbons, 13 of them are carbon 12, one of them is carbon 13. So therefore you need to factor in 14 carbons and then do the same type of calculation as before. And that gives us 7.7%. Okay, so the next thing to do after that is to go down to section K and section L, which are the last parts of the question. So remember, it's C, then H, then alphabetical order after that. So for part II, we're asked to suggest what liquid X might be, and also what gas Y might be. So what we've got to do is look at the 2 formulae. So we can see for allantoin there is 1 less carbon, but we've had 2 oxygens. So that gives us CO2. So liquid X must be derived from H2O, so that gives us H2O2. In the final part of section K, we have to write a balanced equation. So looking at it all, we need to put a 2 in front of the water. So that means our answer to part 3 can now be considered to be that equation. So what we're going to do now is go on to part L, the final part. So that's right down at the bottom, and there's a bit of calculating work coming up here. So you need to have your calculator ready for this one. So what we're doing is processing all the information that we're given in that final paragraph so that we can start using it. So I've covered the dilution factor, what that means, and also the conversion from micromoles into moles. So it's 230 times 10 to the minus 6. So it mentions X. And in the equation it's equimolar to uric acid. So we have to convert to moles per kilogram to the minus 1 of uric acid in vulture tissue. So we take the moles of X as equimolar to uric acid, and we divide it by 1,000 to convert to the number in kilograms, times it by 20, and then that's 4.6 times 10 to the minus 3 moles per kilogram to the minus 1. So we've got the MR of uric acid as 168.22 grams per mole to the minus 1. So multiplying the moles per kilogram to the minus 1 times the MR, it gives us the number of grams per kilogram. So to convert that to milligrams per kilogram, we divide it by 1,000. Sorry, I meant to say multiply it by 1,000. So that gives us 770 milligrams per kilogram to the minus 1. Which takes us to the end of this clip. I hope you found it useful. This question and the previous question in this paper were actually quite hard, but you can look at the examiner's comments to look through where other people made mistakes, and have checked my workings against the mark scheme to make sure that it's correct. Okay, until next time, thanks a lot for listening, and see you soon.